So far in this course, we've covered quite a bit. We've covered first order linear differential equations, where we looked at the case where the first term was by itself. Essentially, this just became your regular integration. And then we looked at the case where we had the first term and the zeroth term. Now this became the case of what we call a linear equation. Next, imagine if we divided this coefficient a1 of x over and we multiplied a function of y. Then we got our case of separable variables, which we covered next. And if we remove the function of x and just had the function of y, then we had our first order autonomous. And now we move on to the topic of this video, which will be exact equations. Now let's say we took our separable differential and rewrote it in the following form. Now this differential could be what we call exact. We don't know that yet. If it is a differential of some function z equals f of xy. And well, how can we kind of see that? Well, the derivative of this function would be this by the multivariable chain rule. Now, in order for these equations to match, we see that dz would have to go to 0. Well, then if the z goes to 0, then this would imply that z would have to go to a constant. And for all this to even hold true, the first partial derivatives in some region in the xy plane have to be continuous. And by the partials we mean df dx and df dy. Well, again, matching our equations, we see that in order for this to hold true, the partials will have to equal as such. H of x equals to df dx and gy equals to df dy. And we have our completeness. We say our differential is exact. In other words, this differential becomes exact, and it is indeed a differential of z equals f of xy, where z equals a constant c, as long as these are met, and of course this is met. Now we can further generalize this to our differential to expand our differential coefficients to a function of x and y, not just x or y by itself. And this is why we kind of started with a separable, so we could build up to this, because the logic translates over, where now we have the following conditions. If they are met, then our differential is exact. Now let's bring this generalization over, clean the slate, so we can go further with this thought. So far what we did, we just showed that a function is exact. But how do we prove that? How do we prove that if the term m is indeed this partial and the term n is indeed this partial, and that they're both continuous first partial in some region? Well, for that we have a criteria for exactness. The exact criteria, without proof, because it is a little bit out of our scope for this video, is that the partial of m with respect to y and the partial of n with respect to x have to equal. And if this is established, then that in essence implies that these are true. Now, one way you can kind of see, this is not really a proof, but it's kind of like an insight on why this sort of works, is if you expand out the equation, we substitute for m and n respectively, we can kind of see that as we sort of rewrite this, that these are almost virtually the same. This term is almost virtually the same as this. The only difference is that the order of differentiation is flipped. Here you differentiate with respect to x, then with respect to y. Here is with respect to y, then with respect to x. But in reality, again, without proof, turns out that this actually ends up being true in mostly all cases when this is true. It's continuous, these are continuous, and then these are continuous, or the same region. Okay? So now we established our criteria for making a differential in that form exact. But now it begs the question, why do we even want to make it exact? Does it help solve our equation in a new manner that is better? Well, let's see that. So we proceed with our solution, which upon solving we should get some function f of xy equal a constant. So once we establish exactness, this is how our solution ensues. We can start with either partial. We can start with m or n. Let's say we start with m, okay? What we do now is we integrate with respect to x. And upon doing that, we get our function f of xy. But we get the antiderivative of m with respect to x. And then we get a constant of integration, a g of y. Now you may ask, why is that a function of y? Why isn't it just a constant itself? Well, one way to think about it is like this, is that we were only given the information of this function. Now in reality, the function f of xy is a function of x and y, but we don't know what some of the y terms look like outside of m. That's why we reserve a function g of y. And one way to see that is by reversing the process. Say we take the derivative of x, the partial derivative. Now g of y would go to 0. And now we would essentially go back to m, what we had before. So proceeding further, that is not what we want to do. What we want is we actually want to differentiate with respect to y. And doing that, we can see that this differential is essentially n. So we write, if we isolate for the g prime y, we get, and now integrating with respect to y, we essentially shall solve for g of y, right here. And we can substitute, and then we get our f of xy. And now in all this, we didn't have to pick m, we could have even picked n. We could have started with this. A similar solution follows, where we integrate with respect to y, the other. Doing so, we get f of xy equals the antiderivative of n with respect to y, plus now our constant integration is with respect to the other independent variable x, so we have h of x. Proceeding further, taking the derivative, not anti, with respect to x, we see that this is essentially m. So we have the following. Now, if we isolate h prime, we get this. And further, integrating with respect to dx, we should be able to plug in for h of x. Okay? And that should get our f of xy. Now, in this whole discussion, one thing I want to point out is this. Is that ideally we could go through this procedure or we could go through this procedure, either or, whichever turns out being simpler. But one hack that you may have noticed is that technically we don't even have to go through the complete procedure for either one. Meaning, what we could do is this. We could essentially do both of them, but we can do both of them from, let's say if we start with m, we do this first, and then we get this. We could just stop right here. And similarly, we could go ahead and do this, and we can stop right here. Now that we would have both of these, this and this, all we need to do is we could look for where these overlap, and depending on where the overlap is, we can solve for g of y and h of x. You'll find that this alternate technique is actually a lot more preferred when these partials m and n are a lot simpler, okay? And you'll see that in a minute. So let's summarize our discussion for exact equations. So step 1 is we ask, could it be exact? Is it of the following form? And if it is, does it lead to some function x of y equals c? Does it? Step 2 is we try to prove that. Is it exact? Now, are the terms m and n equal to the first partials of that function f? Of course, they have to be continuous first partials in some region R. And the way we do that is we have the criteria for exactness. We further take the dm dy equals dn dx, and if that's true, we say it is exact. And once it is exact, we pick the simpler partial and then we integrate. So for example, we could pick the partial m, okay, and integrating we would get f of xy. And then we could differentiate the other to get other partial. So now we would get n. And then we would isolate the integration constant, which is step 5. For example, we get g prime of y. And then we integrate. We get step 6, which would be to substitute the integration constant, because now we have g of y. And upon substituting, we simplify, and we should get our solution. Now, if we're stuck or messy, we could repeat the process, but with the other partials. So instead of m, we could try n, and this should lead to our solution. But alternatively, well, like I mentioned earlier, is we don't need to even go through the whole process. Integrate both partials, get f of xy, and the solution will be the overlap. Okay? And again, this is preferable when our partials are simple. So let us try an example. So we have our following: 2xy squared minus 3dx plus 2x squared y plus 4 dy equals 0. Step 1 is to ask, could it be exact? Is it of the following form: m dx plus n dy equals 0? Indeed it is, because we recognize our terms m and we recognize our terms n. Now the second part is, could it be exact, is would it lead to a function x of y equal to a constant c. Would it? So step 2 is it exact? How do we prove that? Now in order to prove that, the partials m and m have to equal to the first partial of f with respect to x and with f with respect to y. Again, these have to be continuous first partial. The criteria for this is dm dy equals dn dx. So let's check to do that. Let's take dm dy and we get the derivative with respect to y of 2x y squared minus 3, and dn dx is the derivative with respect to x, 2x squared y plus 4. Solving this, we have 4xy equals 4x. And the equality holds, so our condition is met. And now we can see that both these partials, m and n, they're pretty simple. They're not too complicated. So we can do our alternate method where we can integrate both partials and the solution will be the overlap. So let's start with the m. We should get the following. We plug in for m, we have this. Now if we solve that antiderivative, it's pretty simple. It's x squared y squared minus 3x. Now similarly, let's solve for the other. Let's solve for n. Plug in for n, 2x squared y plus 4. And this becomes x squared y squared plus 4y equals the constant with respect to x. Now with these two equations, we can see there's quite some overlap. The overlap is that minus 3x equals h of x, and then 4y becomes g of y. Seeing that overlap and combining it, we have the following. And rearranging or plugging in for f of x by, that is our constant c, we have our solution. One way to verify that this indeed is our solution is to work backwards, is to take the derivative with respect to x. For doing that, we see that we have 2xy squared minus 3, and that is indeed m. And then we can take the derivative with respect to y, 2x squared y plus 4, and that is indeed n. So, for completeness, this is our solution. Now, one aside I want to go over is, are separable variables exact? Well, remember, we had our differential m dx plus n dy equals 0. Now we can simplify to just mx dx plus ny dy. Now this right here is separable. But for this, in this equation, we see that if you use our criteria, we say dm dy equals 0 and dn dx equals 0. But since both are 0, that means both are equal. So this completes our criteria, and indeed separables are exact. So that pretty much covers it for exact. Now let's move our discussion over to equations that are not exact. Meaning that if we started with our equation and we found that it actually did not lead to some function of x of y equal to constant c, so it is non-exact. In other words, we weren't sure if any of the m or n equaled their respective partials. And further, we weren't sure if they're even continuous. And this followed because the criteria for exactness, we say, failed. These didn't end up equaling. Now the question is there a way that we could make these exact? And that is what we will discuss here. Now one hack you can try, it's a theme that you've probably been seeing quite a bit, you've seen for linear equations, is we can multiply a constant mu, and we say that this is our integrating factor. Now if we do this, we can sort of see that this now becomes our new m, and this now becomes our new n. And because of that, in order for exactness, we need the following criteria now. Now our criteria for exactness becomes this. Now if we go ahead and apply the product rule, it expands to this. Let's rewrite the notation. This is kind of a shorter way. So if you have like dm dy, this is a shorter way of writing that, where we use subscript y and subscript x. Solving for mu, we get the following. Now if we assume that this result is in terms of both x and y, then what happens is we get a partial differential equation, where we're not just solving for one solution y, but we're solving for both y and x. But this is of course on ordinary, we're not prepared for that. So we have to limit our assumption to either of x or either of y. So let's say we start with the assumption that is in terms of x. If it is indeed in terms of x, then all the derivatives with respect to y shall go to 0. Well, actually, just mu of y goes to 0 because we're assuming that mu is in terms of x, not m. or not any other term. We're just assuming the mu is in terms of x. So when we're assuming that, that means only mu of y will go to 0. That doesn't imply that this will go to 0. Doing so, we get the following. Now, if we rearrange it, we can see that it is separable. And upon integrating, we shall get our solution in terms of x. And now, if we keep our assumption that mu has to be in terms of x, then that would imply that this quantity inside the integral will have to be in terms of x as well. So, to summarize, what we generally do is we solve for this, m of y minus n of x over n, and we try to see if it's in terms of x. And if it is in terms of x, then our integrating factor shall be this, which is in terms of x. Now, if this doesn't end up being in terms of x, alright, what we could end up doing is we could try our other assumption in terms of y. So let's try that. So similarly, our mu of x, n, we go to 0, and our solution will parallel look as the following. And now, inside the integral, n of x minus m of y over n would have to be in terms of y for this assumption to hold true. So in other words, what we do now is solve for n of x minus m of y over m, and we try to see if it's in terms of y. And if it is, then we see our integrating factor is the following in terms of y. So let's summarize this procedure. Very first step is we establish if it is non-exact, because if it's exact, then we don't really need to do this. So in order to establish that it's non-exact, we see that is it a differential that could be exact, and we establish that no, it indeed does not exact because the criteria for exactness fails. In other words, these do not equal, or these do not equal. Again, assuming that it's continuous or not. And step 2 is, once we establish that it's not exact, we check if the integrating factor first in terms of x makes it exact. So we try to solve the following, and we should get this if it is in terms of x. And if it is not, we could try our alternate assumption, which is check if integrating factor is in terms of y. So we solve for this, and we shall get this if it is in terms of y. And depending on which one we end up getting, is we substitute the integrating factor. So we get this. And now upon substituting, we shall get our solution, because it is made exact, with the new assumption that this is our m, our new m, and this is our new n. And then once it is established that it is made exact, we can execute our procedure for exact, which was earlier in this video. So let's go ahead and do an example. So step 1 is, or step 0 is, could it be exact? Is it of the following form? Indeed it is, because we see our m and we see our n. Now second part is, does it lead to a solution f of xy equal to constant c? So we try to prove that is it exact? So in order for that is, we have to see that m and m equal the first partials of f, where these are continuous in some region. So we go ahead and try to evaluate the criteria, dm dy equals dn dx. So we do that. We plug in for m and we plug in for n. Solving this, we get 6x equals 18x, but this equality does not hold true, so we establish that this is not exact. So in order to make exact, our first step, or step 2 in totality, is check if the integrating factor of x makes it exact. So we solve for this, m of y minus n of x over n. We get 6x minus 18x over 4y plus 9x squared. Simplifying, we get this. Now here, we see that we have the x, but we also have the y. So this is not of x. So what we do now is we check if the integrating factor could be in terms of y. So we solve for this. We get 18x minus 6x over 6xy. Solving this becomes this. The x's cancel out, and we get 2 over y. And this indeed is in terms of y. So this will be our integrating factor, mu y. And we plug in for that term. And upon integrating, we get e to the 2 natural log y plus c, and this simplifies to c y squared. Now step 4, now that we have our integrating factor, step 4 is to substitute for it. Substituting for mu, we should see this. cy squared 6xy dx plus cy squared 4y plus nx squared dy equals 0. The c's cancel, and now we have this. and we see our new m, and we see our new n. To verify that it is exact, we can try to reevaluate our criteria on the new m and n. So we do the following. Solving this, we get 18xy squared equals 0 plus 18xy squared. This equality holds, so we have verified that it is made exact. And now that it is made exact, we shall execute the procedure for exact. Okay? Now, recall that the procedure was we could go either route. We could go the route of m, or we could go the route of n, and we could work all the way through. But we don't need to. We can just simply integrate both partials m and see if f of xy will be overlapped, because in our case here, m and n are rather simple. Okay? So we go ahead and do that. We integrate for m, we get the following. F of xy equals 3x squared y cubed plus our constant with integration, which is gy. And then integrating for n, we do the following. Plugging in for n, we get f of xy equals y to the 4 plus 3x squared y cubed plus our constant of integration of the other independent variable, h of x. Now matching these two equations, we can see that the overlap is such that y to the 4 becomes gy and h of x goes to 0. So now our solution simplifies to y to the 4 plus 3x squared y cubed. And we let f of xy be a constant c. And this right here is our solution.